အားလုံးမင်္ဂလာပါဒီနေ့ကလည်းဆိုသင်ချာကိုအပတ်စဉ်လေးလာနေတဲ့ session လေးပေါ့နော်အခုဆိုရင်လည်းဆိုဒီ metric နဲ့ပတ်သက်တာကိုလည်းဆိုလေးလာနေတယ်ပေါ့နော်အရင်ဘက်ကတော့ဒီ vector နဲ့ပတ်သက်တာဦးစားပေးသွားတယ်အခုဆိုဒီမှာ metric နဲ့ပတ်သက်တာကလည်းဆိုဒီနေ့လုံးမှာကကြတော့ဒီ scalar တွေနဲ့ metric တို့ဘယ်လိုပြီးတော့ linear transform လုပ်မလဲပေါ့နော်အဲ့ဒါလေးတစ်ချက်ကြည့်အောင်နော်
two transformations. Let's say I have two transformations. I have the transformation S, which is a function or a transformation from Rn to Rm. And I also have the transformation T, which is also a transformation from Rn to Rm. I'm going to define right now what it means to add the two transformations. So this is a definition. Let me write it as a definition. I'm going to define the addition of our two transformations. If I add our two transformations, the addition of two transformations operating on some vector x, this is a definition. I'm going to say that this is the same thing as the first transformation operating on the vector x plus the second transformation operating on the vector x. And obviously this is going to end up being a vector in Rm. This is going to end up being a vector in Rm. So this whole thing is going to be a vector in Rm. So we still are, so if we, by definition, this S plus T transformation is still a transformation because it takes an input from Rn. It's still a transformation from Rn to Rm. Now, let me make another definition. Let me define, do it in green, maybe I'll do it in purple. I'm going to define a scalar multiple of a transformation. So I'm going to define, let's say C, where C is just any real number, C times the transformation S of some vector x. I'm going to say that this is equal to C times the transformation of x. This is equal to C times the transformation of x right there. And so similarly, this is the transformation of x obviously is going to be in Rm. So if you multiply any vector in Rm times some scalar, you're still going to have another vector in Rm. So luckily for us, this definition of a scalar multiple, so if I have this new transformation called C times S, this is still a mapping from Rn Rm. This is still a vector in Rm, and this is still a vector in Rn. Fair enough, fair enough. Now let's see what happens if we look at the corresponding matrices for these transformations. We've seen in a previous video that any linear transformation can be represented as a matrix vector product. So let's say that S of a vector x is equivalent to the matrix A times that vector x. And let's say that T of x is equal to the matrix B times a vector x. And of course, since both of these guys are mappings from Rn to Rm, both of these matrices are going to be M by N. Both of these are M by N matrices. Now let's just go back to these definitions that I just constructed. What is S of T of x? Can that then be written as, so let me write it this way, I'll do it in that same color. So you have S, I was going to do it in red. Do it in red. So you have, maybe I'll do it right here. You have S plus T, it's capital T, S plus T of x, I'm just rewriting this up here, is equal to S of x plus T of x, or the transformation T of x, which we now know is equal to these two things. So this is equal to this term right there, the transformation S of x is equal to AX. That's that one right there. And then the transformation T of x is equal to B, the matrix B times x. Now what are these things? And let me write our two matrices in a form that you're probably familiar with right now. Let's say the matrix A is just a bunch of column vectors, A1, A2, all the way to AN. And similarly, the matrix B is just a bunch of column vectors. The matrix B is B1, B2, all the way to Bn, right? These are each column vectors with m components, one for each of the rows, and there's n of these because there are n columns in each of these vectors. So this, when you multiply this guy times, let me make it very clear. If I multiply an x, the vector x is going to look like this. The vector x is going to be x1, x2, all the way down to xn. And we've shown this multiple times. It's a very handy way of thinking about matrix vector products. But we know that this product right here can be written as each of these scalar terms in x times the corresponding column vector in A. I've done this this is probably the 5th video that I'm doing this. So this can be written as x1 times A1 plus x2 times A times A2 all the way to xn times an is equal to this. That's what AX can be rewritten as just as kind of a weighted combination of these column vectors where the weights are each of the values of our vector x. And I have to add this guy to bx. So bx by the same argument, so plus is just going to be, let me do it in the blue, is going to be x1 times b1, x1 times b1 plus x2 times b2 all the way to xn times xn times bn. Now, what is this equal to? Well, we know that scalar multiplication times vectors exhibits the distributive property, so we can just add these two guys right here and factor out the x1, and what do we get? We get this is equal to this whole expression right here. Let me draw a line here because I'm not saying that this matrix is equal to that. I'm saying that this is equal to this is equal to this term plus this term, which is equal to x1. So let me write it, is equal to x1 times a1 plus b1, a1 plus b1, plus x2 times a2, right, I'm just adding these two terms up, x2 times a2 plus b2, all the way to plus, xn times an plus bn. So what is this thing equal to? Well, this is equal to some matrix that some new matrix. Let's define this new matrix. This is equivalent to some new matrix. I'll make it pretty big right here. Times x times our vector x. I'll do the vector x in green. Vector x we know is x1, x2, all the way down to xn. But what is the new matrix going to be? Well, this product is going to be each of these scalar terms times the column vectors of this matrix. So these guys right here are the columns of my matrix. This thing is equivalent to a matrix where the first column right here is A1 plus B1. We're essentially adding the column vectors of those two guys. The second column right here, let me draw a little line right there to show you that these are different expressions. The second one would be A2 plus B2. And then we'll just have a bunch of them, and then the last one will just be an plus bn. So what happens is that by definition, when I added these two transformations, I just used their corresponding matrices, and I said, you know what? The addition of these two transformations created a new transformation that is essentially some matrix times my vector, and that matrix ended up being the sum of the corresponding column vectors of our two original transformation matrices, right? This new matrix that I got, and we didn't, I haven't defined matrix addition yet, but we got here just by thinking about vector addition. This matrix is constructed by adding the corresponding vectors of the matrices A and B. Now, why did I go through all of this trouble? Well, I can make a new definition here that'll make everything fit together well. I'm going to define this matrix right here as A plus B. So my new matrix definition, if I have two matrices that have the same dimensions, and they have to have the same dimensions, I'm defining A plus B to be equal to a new matrix, some new matrix where you add up their corresponding columns. So A1 plus B1, just like what I did here. I don't have to rewrite it all the way up to AN plus BN is the last column. And you've seen this before in your Algebra 2 class, but I wanted to here to do it because this shows you the motivation for it. Because now we can say that the sum of two transformations, so s plus t of x, which is equal to s of x, this is a vector, s of x plus t of x, which we know is equal to, a times x plus b times x, we can now say is equal to, because it's equal to some new matrix, which we can now call a plus b times x, right? I just showed, I mean, this part is from the definition of our transformations and the sum of our transformations that I defined earlier in this video. And then when we just worked this out and kind of expressed these products as products of, or as weighted combinations of the column vectors of these guys, we got to this new matrix. And I defined this new matrix as A plus B. And I did that because it has this neat property now, because now the sum of two linear transformations operating on X is equivalent to, when you think of it as a matrix vector product, as the sum of their two matrices. Now let's do the same thing with scalar multiplication. We know that C times our transformation of X, by definition, I'm saying is C times the transformation of X. So C times whatever vector this is in Rm. And so we know that S of X can be, this right here can be rewritten as AX. So this is C times A times X. And we know that AX can be rewritten as, this is equal to C times the X1 times the first column vector in A, so A1 plus X2 times A2, all the way to plus Xn times An. And what is this? This is scalar multiple. This is just going to be, we can just distribute this C, and then what do we get? We get X, and and multiplication is associative. C is a scalar, X1 is a scalar, so we can switch them around if we want. We know that scalar multiplication is distributive, so we can write this as X1 times C A1 plus X2 times C A2, all the way to Xn times C A n. Now, what is this equal to? This is equal to some new matrix times X. This is equal to some new matrix, let me make that here, times X1, X2, all the way to Xn. And what is that new matrix? What are the columns of the new matrix? Well, the columns are now that, all the way to that. So the columns of this new matrix are CA1, CA2, all the way to CAN. Now, why did I go through this exercise? Well, wouldn't it be nice? I already said that by definition, a scalar times a transformation is equal to this, or a scalar multiple of a transformation is equal to the scalar times the transformation of any vector that you kind of input into it. And of course, that is equal to C times AX. Now, wouldn't it be nice if I could define this thing as some new matrix times a vector x, right? Because this should also be a linear transformation. And this new matrix, I am going to define. This is a definition again. I'm going to define this new matrix as being C times A. So now we have this definition that C times A, if I take any scalar times any matrix A, it's just equal to C times each of the column vectors. And we know what happens when you take a scalar times each of, let me write this, is equal to C times A1, C times A2, I'm just rewriting what I just wrote there, all the way to C times AN. But what is this in effect? We know that when you multiply C times a vector, you multiply the scalar times each of the vector's elements. So this is the equivalent of multiplying C times every entry up in this matrix right here. And like this video, you're probably saying, hey Sal, I already knew how to, in Algebra 2 in 10th grade or 9th grade, I already was exposed to multiplying a scalar times a matrix or adding two matrices with the same dimensions. Why did you go through all of this, trouble of defining the sum of transformations and the sum of matrices? And I went through the trouble because I wanted you to kind of understand that there's nothing, I mean, it is natural, but there's nothing about the universe that said matrices had to be defined this way. Matrix addition or matrix scalar multiplication or the addition of two transformations. I wanted you to see that it's all kind of the mathematical world has constructed it in this way because it seems to have nice properties that are useful. And that's what I've done in this video. In the next video, I'll do a couple of scalar multiplications and matrix additions just to make sure that you remember what you had learned in your 9th or 10th grade algebra class, but you'll find that the actual operations are almost trivially simple. Let's say I have two.
ဒီမှာတော့ LS အမြင်ပေါ့နော် LS ဆိုကြည့်နေတာဒီဟာကတော့အရန်ခတ်တဲ့ဟာတော့မဟုတ်ပေါ့နော် LS ဆိုကိုယ်တိုင်လည်းအရင်တော့ဘယ်မှာလဲညီမလေးတို့တွေလည်းတကယ်လို့ကိုကဒီ first year မှာပဲဖြစ်ပေါ့နော် second year မှာဖြစ်ဒီဟာလေးတွေကပြန်ပြီးတော့လုပ်ခဲ့ရဘူးလေပေါ့နော် LS ကိုယ်တိုင် LS ဒီရတဲ့လောက်ဆိုရင် LS first year မှာဒီ metric နဲ့ဟာပတ်သက်တာနည်းနည်းပြန်ပြီးတော့အဲ့လိုမျိုးဒီ process တွေလိုက်ပြန်လေ့လာရတယ်ပေါ့နော်အမှန်ဆိုဒီဟာတွေကလည်း10တန်းအားလုပ်ခဲ့တဲ့ဟာတွေပါပဲ trade ထူတော့မဟုတ်အဲ့လိုဆိုတော့ဒီဟာပြန်ကြည့်မယ်ဆိုရင်ဒီဟာအဲ့လိုဆိုဒီ transform လုပ်နေတာပေါ့နော်အဲ့လိုဆို machine learning နဲ့ပြန်ပြီးတော့ချိတ်ဆက်မယ်ဆိုရင်ပေါ့နော် machine learning မှာဆိုတော်တော်များများက data point of view ကပဲကြည့်ကွာ data point of view ဆိုရင်ဒီက real world problem တော်တော်များ data ရဲ့အဲ့လောက်ရှိတာမဟုတ်တယ်ဟုတ်တနည်းမဟုတ်တနည်းကွာ तू ကပြီးနောက်တစ်ခုက dimension reduce လုပ်မဲ့ခါမျိုးတွေပါအဲ့လိုမျိုးဆိုရင် transfer လုပ်ပြီးတော့မှရမှာဟုတ်တယ်ဟုတ် dimension ကအခုလို့300နဲ့300ရှိရဆိုပါဆိုတော့အဲ့လိုဆိုတော့ကွာ300နဲ့300ရှိတဲ့ဟာကြီးကိုသွားပြီးတော့ machine learning ကိုသွားပို့ဆိုတာမသိပြီးတော့မကောင်းဘူးပေါ့နော်လို့ဆိုတော့လိုအပ်တဲ့အရေးကြီးတဲ့ information လောက်အရင်ဆုံးဆွဲထုတ် convert လုပ်တဲ့ပုံစံမျိုးလုပ်လိုက်တဲ့ပုံစံမျိုးပဲထားပါတော့ပြီးတော့မှဒါလည်းသွားပြီးတော့ transfer လုပ်တဲ့ process ကလိုအပ်လာတယ်ဆိုမြင်မှမဟုတ်ဘူးနော်အဲ့မှာဆိုရင်အဲ့ဒါဆိုခုလုံးနေ operation တော်တော်များများကြာ metric တွေ beta အဲ့ဒါတွေပဲလုံးဝ number တွေပဲသွားပြီး calculate လုပ်နေတာဖြစ်တဲ့အတွက်ပေါ့နော်အဲ့လိုဆိုဒီ operation တွေကိုပြန်ပြီးတော့မြင်သာထင်သာရှိလာစေခြင်းတယ်ပေါ့နော်ပြောချင်တာဒီ image ကိုပဲဖြစ်ဖြစ်ဒါမှမဟုတ်အခုလိုဒီက transformation နဲ့ပတ်သက်တဲ့သတိထားမိတာအများဆုံးကဒီ computer vision step မှာပေါ့နော်တော်တော်များများလုပ်ကြတယ်တခြား structured data ကိုကတိတ်ပြီးတော့အဲ့ဒါမျိုးမရှိဘူးပေါ့နော်ဒါဆိုဒီ time series prediction တွေပါလို့တဲ့ခါမျိုးကြာရင်ဒီ transformation က not very good thing ပေါ့နော်ဒါပေမဲ့ computer vision ကိုလုံးဝလို့ vision field ကိုသွားတဲ့လူတွေအတွက်ဆိုရင်ဒီဟာလေးကလုံးဝသိတဲ့ field ပေါ့နော်ဆိုတော့ video တွေ image တွေ processing လုပ်တဲ့ခါကျရင် transfer image တွေကိုဘယ်လိုလုပ်ကိုလိုချင်တဲ့အောင်ဘယ်လို transfer လုပ်ရမလဲပြီးတော့ dimension ကိုဘယ်လို reduce လုပ်ရမလဲကိုယ့်ရဲ့ model ကိုဘယ်လိုပေးရမလဲအဲ့လိုလုပ်တဲ့ဟာတွေတော်တော်များများသူ့အဲ့ဒီ end သူ့ရဲ့ backbone ကိုကြည့်မယ်ဆိုရင်ဒီ metric formulation ကိုသုံးထားတယ်ဆိုတဲ့သဘောမှရှိတယ်ပေါ့နော်အဲ့လိုဆိုဒီ formula လေးကမှန်ဆိုတော့ဆိုငယ်တဲ့ကလိပြီးသားတဲ့ဟာတွေပေါ့ trade ထူတော့ဘာမှမရှိဘူးဒါပေမဲ့ဒီချိန်မှာလည်းစာနေပြောတဲ့အတိုင်းပေါ့နော်ဖြစ်နိုင်ရင်သူ့ intuition ကဘာအတွက်ငါလာကိုလေ့လာနေဆိုပုံစံမျိုးအများပြန်တွေးပေါ့နော်ဒီ transformation တော့ဟုတ်ပါပြီ linear transformation ကဘာလို့ငါပြန်လေ့လာဖို့လိုအပ်တယ်လဲဆိုရင်ဟာ reasoning ကိုလည်းပြောပြတာပေါ့နော်ဆိုတော့ linear transformation ကပြောရမယ်ဆိုရင်ဒီကအဓိကဒီက linearly dependent ဖြစ်နေတယ်ဆိုရင်လည်းဆိုတာတိတ်အရေးမပါတဲ့ information လို့လည်းဆိုယူဆလို့ရတယ်ဟုတ်တယ်ဟုတ်လည်းဆိုတော့အရင်တော့ဒီ better lesson ရကြည့်မယ်ဆိုရင်ပေါ့အဲ့လိုဆိုတော့တကယ်လို့ဆိုတာဒီကိုက transfer လုပ်တဲ့ခါကျရင်ကိုက okay အရေးကြီးဘူးလေ HD တဲ့ပုံစံမျိုးပဲဆိုပါဆိုအဲ့မှာဆိုအရေးကြီးတဲ့ line လေးတွေပဲကိုက transfer လုပ်ပြီးယူပြီးတော့မှ model တော့ပြလိုက်တာပို့ပြီးတော့အချိန်နဲ့တက်တာရတယ်ပြီးတော့ကို model လည်း processing power တိတ်ပြီးမသုံးရဘူးเนาะ internal cost wise ကိုကြည့်မယ်ဆိုရင်တော့ cheaper ဖြစ်တယ်လို့ပြောတယ်ပေါ့နော်ဒီလက်ဆိုဒီတကယ် real life application တစ်ခုကိုလုပ်မယ်ဆိုရင် project တစ်ခုပဲလုပ်ဖြစ်ပါပြီသူ့ရဲ့ cost ဆိုတာအများကြီးရှိတယ်ပေါ့နော် time cost ရှိမယ် resource cost ရှိမယ် charge case cost ရှိအများကြီးရှိပါတယ်လားအဲ့လိုဆိုတော့ကိုယ့်ဘက်ကတစ်ခုကို eliminate လုပ်လိုက်တာနဲ့ကိုယ့်တို့အများကြီးတာတာအဲ့လိုမျိုးဟာလေးတွေအများကြီးရှိတယ်ပေါ့နော်အဲ့လိုဆိုတော့ဖြစ်နိုင်လို့ရှိရင်ဒီမျိုးဟာလေးတွေကဒီဟာလေးတွေကဒါ tool အနေနဲ့မျက်စိရမြင်စေချင်တယ်ပေါ့ဒီလိုလုပ်လို့ရပါရဲ့လားဆိုတဲ့ဟာမျိုးလေးပေါ့ transfer လုပ်လိုက်ရင်ငါတော်တော်လေးကြိုးရှိပါလေဆိုတော့အမြင်လေးကိုမြင်စေချင်ပါတယ်လို့ဒီဟာနဲ့ပတ်သက်ပြီးလဲဆို question လေးတွေမေးကြရှိလားမေးပါအောင်အဆင်ပြေကြလားညီမလေးရင်ထူအဆင်ပြေလားညီမလာတော့အရင်ခတ်တဲ့အဆင်ပြေကြတာတော့မရှိဘူးလေဆိုရင်တော့မြင်တယ်ပေါ့နော်ဒါရိုးမလို့ကတင်ချာနဲ့ပတ်သက်ပြီးလဲဆိုမြန်မာတွေကငါတုံးနေကြအောင်မပါဘူးပေါ့နော်တင်ချာတစ်ခုပြတွက်နီးလောက်က how to လောက်ကလူတိုင်းလို့သိတယ်ပေါ့နော်ပြောချင်တာအဲ့လဲဆို how to ကိုသိပြီးတော့ body မရှိဘူးပေါ့နော်အဲ့လဲဆိုမြန်မာတွေကငယ်လေးကလေးကနေပြီးတော့ how to ကိုလဲဆိုတာ memorize လုပ်ပြီးကြီးပြင်းခဲ့တာဖြစ်တဲ့အတွက်ကိုယ်တိုင်လည်းပုံစံပေါင်းများစွာတွက်ပြီးတော့ကြီးပြင်းလာခဲ့တာဖြစ်တဲ့အတွက်ကိုအုံနောက်မှာ how to ကနီးလေးပြလိုက်ကွာလုံးနိုင်လူတွေပဲပြောနေတာအဲ့လိုရရင် difficulty ဖြစ်နေတာဟာဘယ်လိုလုပ်ရမလဲဘယ်လိုကိုင်းမလဲမသိရလို့မျိုးမရှိကြဘူးအဲ့ဒါစီဒီ personally experience ရပါတော့ဆိုတော့အဲ့ဒါဆိုနိုင်ငံခြားမှာအကြောင်းလာတတ်တော့ဗာသတိထားမိလဲဆိုပေါ့နော်အဲ့ဒါဆိုမြန်မာနိုင်ငံကအကြောင်းသားရင်းနဲ့ foreign country အကြောင်းသားရင်းနဲ့ရှင်းနိုင်ဘယ်နေရာတာနေလဲဆိုအဲ့ဒါဆိုတာဒီမှာ excite နေမှာလို့ဆိုအရန်တာတယ်အဲ့ဆိုနီးပြတယ်လို့ဆိုအမြန်လုံနိုင်တယ်သိရမလားသူများတို့လိုမျိုးသိရမလားနီးဒါပေမဲ့နီးကိုဘာကြောက်ပြလဲ reason လားမသိကြတာကွာနီးပြလိုက်လို့လိုက်တယ်ကြတာပဲဟုတ်လား question မထုတ်ရတဲ့အကျင့်တွေတစ်ခုပဲရှိတယ်မြန်မာတွေကလေဒါကလည်းပြောချင်တာလဲဆို education system အရလို့လည်းပြောလို့ရတယ်ဘောနော် question ကိုသိပြီးတော့ဦးစားမပေးတာဖြစ်ခဲ့တဲ့အတွက်ဒီကလည်းဆိုတာ how to နဲ့ကြီးပြင်းလာခဲ့တာဖြစ်တဲ့အတွက်တော်တော်များများ how to နဲ့ပတ်သက်တဲ့ expert တွေပဲသိတယ်ဒါပေမဲ့ why ဆိုတဲ့ question ကိုဘယ်သူမှမဖြေနိုင်ကြဘူးပေါ့နော် most of the time ပြီးတော့အခုကဒီ mindset ပေါ့နော်နည်းနည်းဘယ်လိုဖြစ်နေလဲဆိုတော့ နည်းနည်းကြောက်တဲ့စိတ်တွေအရင် shine နေဆိုတဲ့စိတ်တွေတခုအဲ့နှစ်ခုအဲ့လက်စတကပြင်နေတာအဲ့နှစ်ခုပေါ့နော် mindset ပေါ့နော်ဘာဖြစ်လဲဒီ why question မေးတတ်အောင်ရယ်ပြီးသွားရင်ကိုမားတာကိုမကြောက်နိုင်ဘူးမားရဲဆိုတာမှဆိုတော့ open ဘူးမကိုလုံးဝဒီကဒီချက်မှာကိုကြောင်းတာကွာကိုမားလို့ရှိရင်ဘယ်သူမှကိုအပြစ်ပြောမယ်ဆိုတော့တယောက်မှမရှိဘူးဒါပေမဲ့အဲ့ဒီဟာလေးကိုအုံတော့တယ်မဝင်ကြဘူးနော်တော်တော်များများမားမအောင်ကြောက်နေကြတယ်ကိုရမ်းလိုက်ပြီးလို့မားရောအဲ့ဒါမျိုးလေးလည်းဆိုအဓိကပြင်ကျင်တာပေါ့ trade သူအဲ့နှစ်ခုပါလေဆို intention ကဆိုတော့တော်တော်များအစားမလုံးနိုင်အဲ့မောင်လေးညီမလေးတွေကလက်ထက်အရန်ညံကောင်းတဲ့လူတွေပဲလက်ဆိုရင်ကိုကိုညံကောင်းတဲ့စင်မှာတော့မရှိဘူးငပိန်းလို့ယူဆရတဲ့စင်ဆိုတော့လေတော်တော်များဆိုသူများတစ်ခေါက်ပြောရဲဆိုတော့3-5ခါလုံးမှာသတိသိတဲ့လူမျိုးပေါ့နော်ပြောချင်တာ intent or အဲ့လိုမျိုး intelligent ပေါ့နော် IQ လို့သဘောထား IQ အနေနဲ့ကြည့်မယ်ဆိုမြန်မာလူတွေကအရန် IQ ကသူများတဲ့မမြင့်ဘူးဆိုတာကသူများတဲ့နှိပ်တာတရားမှမရှိဘူးပေါ့နော်အဲ့လိုမျိုးဆိုတော့ကိုကိုတိုင်းစာလုပ်ချင်တဲ့ဒီရှိတဲ့လူတွေတော်တော်များ IQ ကအနည်းဆုံး above average ကရှိကြတာအဲ့လိုဆိုတော့ကွာဒီကဒီ mindset လေးပဲနည်းနည်းပြင်ယုံပဲပေါ့နော် mindset လေးပြင်သွားကိုကိုကတိုးတက်ဖို့အရန်လွယ်တယ်ပေါ့နော်ဟုတ်ပါပြီ sorry ပါလို့ Brian ရှိ organ ထိရုံပဲဒါလမ်းကြောင်းလွဲတယ်ဆိုပြီးပြောခံရမြင်အောင်လေအဲ့လိုသွားအောင်ဒါတော့လည်းဆိုဒီဟာသူ Isabel လေးနဲ့ပေါ့မျက်စိတွေတေချာလေးမြင်လာအောင်လို့လေသူကပြောပြရဆိုသဘောလေးပေါ့နော်ကဲစရအောင်လို့ဒါကဒီဗီဒီယိုနှစ်ခုပဲဦးစားပေးသွားမယ်ပေါ့နော်ဒီနေ့ကလည်းဆို matrix multiplication ကိုတေချာလေးတစ်ချက်ပြန်လုပ်ပြန်ပြီး exchange ပြန်ယူလို့ဆိုသဘောပေါ့နော်
Started off with two linear transformations. We had the linear transformation S that was a mapping from Rn to Rm. And then we had the linear transformation T that was also a mapping from Rn to Rm. And we defined the idea of the addition of these two transformations. So S plus T, this transformation of X, we defined as being equal to S of X, this vector, plus T of X. And of course, this will be in this input is still from Rn, and then each of these are vectors in Rm. If we add two vectors in Rm to each other, we get another vector in Rm, because Rm is a valid subspace. It's also closed under addition. So this is still a mapping. So S plus T is still a mapping from Rn to Rm. And we also said that, look, every linear transformation we've shown in a previous video can be represented as a matrix. That we could say that S of X is equal to some matrix A times X. And we could also say that T of X is equal to some matrix B times X. And both of these would be M by N matrices. And let me write that, M by N, both of these. Because these are both mappings from Rn to Rm. And what we did is we made another definition. We defined, this was a definition right here. Then we made another definition. We defined the addition of two matrices. We said the matrix A, this is any matrix A plus B, they both have to have the same dimensions. So they're both M by N in this case. And we defined this addition to be a new matrix where each column of this matrix is the sum of the corresponding columns of these matrices. So this matrix's first column will be the sum of A's first column and B's first column. So A1 plus B1. The second column, I'll do a little line here, is A2 plus B2. And it goes all the way to AN plus BN. This was a definition. And the whole reason why we made this definition is because if you defined matrix addition in this way, then this thing, when you replace it with AX plus BX, you get to that this thing over here is equal to the corresponding matrices by this definition, A plus B times X. This was the motivation to get to a nice expression like this for defining matrix addition in this way. Now this all seems very abstract, so let's actually add a matrix, or let's add two matrices. So we'll start off with a 2 by 2 case. So let's say I'm adding the matrix 1, 3, minus 2, 4 to the matrix. Remember, they have to have the same dimensions. To the matrix 2, 7, minus 3, minus 1. What do we get? Well, by definition, you just add up their corresponding columns. You add up the first column. When you add up the corresponding columns, what happens when you add up two columns, two vectors? Well, you just add up their corresponding entries. So essentially, when you add up two matrices, you're just adding up all of the corresponding entries. I'll talk about it in this way just because that's how I define it, but they're all equivalent. So we'll go the first thing. The first column in this matrix right here is going to be this column plus this column. So it's going to be 1 plus 2. Let me write it like this. 1 plus 2. And then minus 2 minus 3. Minus 2 minus 3. And then the second column, that one right there, is going to be 3 plus 7. 3 plus 7. And then 4 minus 1. 4 minus 1. And so this will be equal to 3, 10, minus 5, and 3. Just like that. And notice, even though the definition is I'm adding up corresponding columns, well, what in effect happened? Well, I'm just adding up the corresponding entries. I added the 1 to the 2, the 3 to the 7, the minus 2 to the minus 3, the 4 to the minus 1. It's that straightforward. Nothing fancier than that. In fact, we could have rewritten this definition. We could rewritten this definition if we say that the vector or the matrix A is equal to, A11, A12, all the way to A1n, and then if you go down, this is A21 all the way to AN1, and you go all the way down there to ANN. We've seen that before. And then the matrix B, just by the same argument or by a similar definition, is this B11. That entry is B11. That's B12 all the way to B1n. This is B21, second row, all the way down to BN. This is M. We have M rows, so this is MN. So this right here is BM1. This would be BM2, all the way down to this is BMN right there. I want to be very careful. These are M by N matrices. So this row down here is the mth row in both cases. But we could redefine our matrix, or another way of stating this matrix addition definition is to say, look, if I'm going to add A plus B, I'm just going to add up the corresponding entries. So this entry up here is going to be, do a different color. It's going to be A11 plus B11. This one's going to be A21 plus B21, all the way down to AM1 plus BM1. And then this is going to be, of course, A12 plus B12, all the way to A1N. Let me scroll over a little bit. All the way over to A1N plus B1N. And then all the way down to AMN plus BMN. These are equivalent definitions. This takes a lot less space to write in. I felt comfortable doing it because we've already defined vector addition. But it essentially boils down to you just add up all of the corresponding entries. That's all matrix addition is. It's probably one of the simplest things that you've seen in your recent mathematical experience. Now, matrix scalar multiplication, very similar idea. We defined scalar multiplication times the transformation of x to be equal to a scalar times the transformation of x. This was a definition. And we also defined scalar times some matrix A to be equal to the scalar, a new matrix where each of its columns are the scalar times the column vectors of A. So A1, and then the next column is CA2, and then you go all the way to CAN. And the whole motivation for this was because this could be simplified to, well, T I said was equal to Bx, the transformation, this is A times transformation of x. The transformation T of x was equal to, so this we still have our C, so it's going to be C times the matrix B times the vector x. That's what the transformation of x could be written as. And so this would be equal to, so if I use this would be equal to, by just manipulating, and we did this in the last video, by actually breaking this up in the column vectors, multiplying them by each of the components of x, and then distributing the C and rearranging a little bit, we can now say, using this definition, that this is equal to some new matrix CB, we're using this definition. Some new matrix CB where it's essentially C times each of the column vectors of B times X. This right here was our motivation. We wanted to be able to express this as a product of some new matrix and a vector, because any linear transformation should be expressible in that way. That's why we made this definition. Now let's apply it, and I wanted to show you that this is perhaps even simpler than matrix addition. So if we want to multiply the scalar 5 times the matrix, I'll do a 3 by 2 matrix. So 1, minus 1, 2, 3, 7, 0. This will just be equal to, by this definition, I'm just saying, look, I'm multiplying the scalar times each of the column vectors. So it's 5 times 1, 2, 7. What's that? That's just 5 times each of the entries. So it's 5 times 1, which is 5, 5 times 2, which is 10, 5 times 7, which is 35. Then the next column is going to be 5 times this column right here, which is just 5 times each of its entries. So 5 times minus 1 is minus 5. 5 times 3 is 15. 5 times 0 is 0. It's that simple. You literally, if we go back to this definition, we can define scalar multiplication of a matrix. So we could also define CA as being equal to, if we say this is a representation for A, of the scalar C times each of the entries of A. That's it. So it's C times A11, C times A12, all the way to C times A1n. You go down this way, C times A21, all the way down to C times AM1. And if you go down the diagonal, it's be C times AMN. You literally just take your scalar and multiply it times every entry in A, and that's all you have to do. So hopefully this clarified things up a little bit, or maybe it was a bit of a review from things you might have learned in high school.
ဟုတ်ပါပြီဒီဟာလည်း trade ထူးတော့လဲဆိုတော့ဘာမှရှိရလို့တော့မမြင်ဘူးပေါ့နော်တခြားကောက်ကိုကြည့်နေမောင်လေးညီမလေးလည်းရှိရဆိုတော့လေဒီဟာတမင်သက်သူက Isabel လေးကိုပြန်ပြီးတော့ပြောရဲဆိုတဲ့သဘောလေးပေါ့ဒီဟာလေးနဲ့ပတ်သက်လဲဆို question လေးတွေမေးကြရှိလားအဆင်ပြေတာမောင်လေးထောက်ခံနေအဆင်ပြေလားဒီဟာလေးကိုလေ
ကျွန်တော်ခုမှ join ရတော့
ဟုတ်ပြီပြီးကြည့်လိုက်နော်လို့ဆိုဒီမှာပဲအံမို့ဟုတ်ပြီနော်ပြီး recording နဲ့ကြည့်လိုက်နော်မောင်လေးနော်
ခုမှမီးလာလို့
okay no worries ဒါလည်းဆိုဗာလေမောင်လေးကြောက်တယ်မောင်လေးအဆင်ပြေလားမောင်လေး
ဒီမှာကျွန်တော်လည်းမီးရပြည့်လိုက်လိုက်ဖြစ်တော့တိတ်ဆုံးလဲကြည့်မြအောင်
ပြည့်လို့ဆိုရအောင်လေနော်ညီမလေးရင်ထော်ညီမလေး
ဟုတ်ကဲ့ပါ
ညလူလဲနေတော့လေနော်မောင်ညီမလေးနော်ဟုတ်ပါအားလုံးလည်းဘိုင်ဘိုင်ပါလို့ခဏလေးပြန်တွေ့ကြမယ်နော်အဲ့ဒါဆိုနောက်ဆက်ရှင်တစ်ခုရှိတော့လေ
ဘိုင်ဘိုင်ပါ